Let us consider the computation of DFT of a sinusoidal sequence of finite length, and we are going to implement it using Matlab. We will run the Matlab program. During execution of the program will ask the user to input the data. First is length of the DFT n, then sampling period t in second. So sampling period is nothing but 1 upon the sampling frequency, and frequency of the sinusoidal signal in hertz. So the first case which we are going to implement is we will be inputting the number of points of the DFT 32 point. Then the sampling frequency we are considering 64 Hz. So the sampling interval is 1 upon 64 second. And frequency of the sinusoid we are going to consider 10 Hz. Then we are going to plot the magnitude of the DFT samples. So this is a Matlab program in which we are giving the input command to input the number of points of the DFT n, then the sampling period t, and the frequency of the sinusoid. Then we are defining the sinusoidal signal frequency, that is the sampled signal using a sine function. Then we are taking the DFT of that signal, and then we are plotting the DFT of that signal. So let us run the program. So in command window, the program is asking me to type the length of the DFT. So I'm inputting 32. Then type the sampling period. So I will be inputting 1/64, and type the frequency of the sinusoid. So we will be considering the frequency 10 Hz. So I'm inputting 10. So as you see, this is the DFT plot, that is the frequency component which you are observing. On y-axis it is mod x of k, and on the x-axis it is k, that is the frequency bin. And as you see, the DFT frequency component we are observing at k is equal to 5 and k is equal to 27. As the sampling frequency is 64 Hz, it is greater than 20 Hz. 20 Hz is the Nyquist frequency, that is 2 into 10 Hz. So the aliasing will not occur in this case after sampling. Since the time domain sequence is a pure sinusoid, its discrete time Fourier transform contains two impulses at frequency plus minus 10 Hz, and the plot contains two impulses at f is equal to plus minus 10 Hz, and elsewhere it is 0. So discrete time Fourier transform, as we know, it is a continuous function of frequency. So it is sampled at omega is equal to 2 pi k upon nt to get the discrete Fourier transform. So if we expand omega, that is 2 pi f. So I will simplify this expression so that we will get f is equal to k upon nt. Therefore, 32-point DFT is obtained by sampling DTFT at frequency f is equal to k upon nt. So I am substituting the values. N is 32 and t is 1 upon 64. So we will get ultimately it will be 64 k upon 32. So it is 2 k. where k is varying between 0 to 31. Therefore, the impulse at frequency 10 Hz, it appears at the frequency bin of DFT. What is the frequency bin location? K is equal to 5. Suppose I take frequency 10 Hz over here. So what will be the K value? 10 upon 2. So that will be K is equal to 5. And therefore the impulse at frequency minus 10 Hz, that is for the negative frequency, it will appear at the bin location K is equal to, how many points are there? 32 point minus 5. So it is bin K is equal to 27. So the DFT has correctly identified the frequency of the sinusoid in this first case. The first half of the DFT samples. So there will be K will vary from 0 to n by 2 minus 1. So what is n? 32 upon 2. So that is 16 minus 1. So 0 to 15. It corresponds to the positive frequency axis from f is equal to 0 to f is equal to fs by 2. So what is fs? Sampling frequency is 64 Hz. So 64 upon 2 is 32. And it is excluding the point fs by 2, that is 32. And the second half for k is equal to n by 2 to n minus 1. It corresponds to the negative frequency axis from f is equal to minus fs by 2 to 0. Now let us consider the second case. We are going to input n is equal to 32 point DFT. Then the sampling interval again we are keeping the same, that is 1 upon 64 second. But now in this case we are going to change the frequency of the sinusoid. Instead of 10 Hz we will be considering 11 Hz, and we will be plotting the magnitude of DFT samples. So the same Matlab program we will be using, only while inputting the input values we will be inputting the same value of n and t, but we are going to uh, input the different value of the sinusoid. Now the same Matlab program I will execute. So let us run the program again. Now in command window, as you see, type the length of the DFT. So again I am inputting 32 point DFT. Then the sampling interval I will be inputting sampling period 1 upon 64 second, and type in the frequency of the sinusoid. I will be inputting 11 Hz. So this is what is the DFT plot. As you see, in the previous DFT plot, the other frequency bins, the magnitudes were 0, but now we are getting a non-zero amplitudes of the frequency components in the DFT plot. Now, since the time domain sequence is a pure sinusoid, the discrete time Fourier transform contains two impulses at frequency plus minus 11 Hz, and it is 0 everywhere else. However, the frequency locations are between the bins k is equal to f by 2. So what is f? It is 11 Hz upon 2, which is 5.5. That is between k is equal to 5 and k is equal to 6. And k is equal to 26 and k is equal to 27. The bin locations 5 and 6, they correspond to the frequencies. Now we are going to consider frequency is equal to k upon nt. As in the previous slide we have seen this formula. So the first frequency, that is if I consider k is equal to 5. So I will substitute k is equal to 5 upon n is 32 and t is 1 upon 64. So this 64 will come in the numerator. So I will get the first frequency 10 Hz. and the second frequency, it is 12 Hertz. So the bin locations 5 and 6 corresponds to the frequencies 10 Hz and 12 Hz respectively. Therefore, the frequency of the sinusoid is exactly halfway between these two bins. Now, as we have seen in the frequency plot in the case 2, that there is a spread of energy from a single frequency to many DFT frequency locations, because at every frequency bin, the magnitude was non-zero. So there is a spread of energy we have seen at from a single frequency to many frequency locations, and this is called as a spectral leakage. So the conclusion of this experiment is we have implemented the spectral analysis of finite length sequence with 10 Hz and 11 Hz sinusoidal frequencies, and we have sampled these sinusoidal frequencies at 64 Hz and we have taken 32 point DFT. The DFT components plot we have observed to understand the spectral leakage.